Good day, ladies and gentlemen, and we meet yet again. We see each other, and we are back, trying to learn as much as we possibly can about physical science. From your comments, this is the one question that you were anticipating the most. How to calculate that Kc. In this case, I'm going to, and I've taken this from the Gauteng paper. And I just will try to explain it in as a simplified manner as much as I possibly can. And please don't forget to subscribe to our channel, become part of the family. Okay. And if you just need assistance, with the lessons either in mathematics or physical science, please don't forget to send us an email. And our email address is info@mlungisinkosi.co.za. All right, let's dive right into the question. So they say we've got steam that reacts with hot carbon, that is 1,000 degrees according to the following reaction. They say initially we've got 36 grams of steam at a certain amount of carbon. So they don't give us that amount. That's sealed in a container and allowed to react. So this tells you that you didn't have products formed at the beginning. It makes sense. Reactants had only started reacting, right? And then they say it is found that the amount of carbon changed by, right? There's a very big difference. We'll explain that a little bit later. 0.225. And then they say, first of all, define the term dynamic equilibrium. Please remember, we say this is when the rate of the forward reaction is equal to the rate of the reverse reaction. Remember that. Okay, I'm not going to write it down. I'm very lazy. Okay. They say calculate the equilibrium constant for this reaction. So what I'm going to do is I'm going to just quickly draw that table for us. Okay. So that we know how to navigate our way through that. Okay. So I've got two reactants and two products. So I'm going to make provision for them. And by the way, I know some of you prefer to write that ratio there. Okay, nothing wrong with that. So this is initial, that's in moles. Please don't forget to write the SI units. Okay, that's change in moles. Okay, and that's equilibrium. That's also in moles, as well as this last row where we've got concentration, equilibrium concentration, and that's in moles per cubic decimeter. Sorry for squeezing it like that, but I'm sure you understand. All right, so what do we have? We've got 2 H2O, okay, and I've got 1 mole of carbon. I've got 2 hydrogens that are formed there. I've got 1 carbon dioxide that is also formed. All right, so let's start with what we have. They said initially we've got 36 grams of steam. Steam, that's H2O. So I'm going to find the number of moles. We're given that in grams. So number of moles, remember initial, I want only moles. So that's mass over molar mass. This is going to be, our mass is 36 grams divided by molar mass. I want you to please note, it's the molar mass of steam, which is water, H2O. Please, when you calculate the molar mass, you do not include that coefficient there. The only thing that we multiply by is the subscript there, because it tells us about the number of hydrogen atoms. So this means it's 2 hydrogen atoms bonding with 1 oxygen atom. So that's 2 hydrogens, 1 oxygen. So that would be 2 times 1 from the periodic table plus oxygen, which is 16. So that will give us 18. So this is 36 divided by 18. That will give us 2 moles. Okay. So in this case, it means we started with 2. All right. And then they said it reacted with a certain amount of carbon. If you don't mind, I'm just going to call that X. We don't know what that amount is. But remember, did they say anything about our products at the beginning? Nope. So it means that we assume that we started with nothing. Okay. And then they said at equilibrium, we found that the amount of carbon changed by 0.225. Okay. Now there's a difference between saying changed to 0.225 and saying changed by 0.225. And what's that difference? The difference is that when I say changed to, it means this would be my result. It changed to that result, okay? But if I say I changed by, it means that something happened that changed whatever I had by that amount so that I will get whatever result that I have. Now, it means, I want you to please understand this. So it means that this amount that it changed by is the amount that took part in the reactant. This is what it actually, this is the amount that reacted during the course of the collision. I hope that makes sense, ladies and gents. Né? Okay, so this is going to be, so it means that the amount, all right, in fact, let me use a different color because I always prefer that in this second column, because remember, this is where the reaction takes place. So it means that this reaction here, the amount of carbon that was used is 0.225. Okay, I squeezed my numbers quite tightly there. I should have actually made my table a bit bigger. Right, so this amount was 0.225. Now remember, ladies and gents, please, this is where we are now going to use the ratio. Okay, so now what I'm going to do is I'm going to say, well, how much, if I reacted 0.225 moles, right? How much water reacted? So I'm going to say for every 2 moles of water, how many moles do I use of carbon? 1, right? So look at this. Let's use ratio and proportion. For every 2 moles of H2O, I'm going to use 1 mole of carbon, right? So my question is, for how many moles am I going to use 0.225? And note, same things on the same side. For every 2, there's 1. For how much will I have 0.225? So for how much will I have 0.225? Can you see that? So let's cross multiply. 1 multiplied by x will give me x. Okay, 2 times 0.225, this will give me 0.45. Okay, right, so it means the amount of moles of H2O that I would have used is 0.45. Okay, and the same thing is true here. For every 1 I use 2, right? So for how much will I use for 0.225, how much of that will I use? It will be exactly the same amount. Or if you want to, you can use this one. For every 2 there's 2. So for 0.45 there'll be 0.45 as well. Okay, please, I want you to note that. So this is where we use our ratios, right? And then again, I'm going to say, well, for every 1 carbon, I get 1 carbon dioxide. So for 0.225, how much do I get? I get 0.225. So it means for the same amount of carbon I use, I produce the same amount of carbon dioxide. So as a result, for 0.225, I will produce 0.225. Okay, so I hope that makes sense, ladies and gents. Right, so now look at how logical this will be now. I started with 2 moles. I use, or you can say I change by 0.45, right? How much do I have at the end? Of course, this is going to be 1.55. Why? Remember, I use my reactants, right? But I form products. So these ones, I will say whatever initial I start with, I subtract that, the amount that I changed by, and I get the amount at the end. The same thing here. I start with an X amount, I change by 0.225. What do I have at the end? It's X minus 0.225. Okay, right, I hope you understand that. And then what about here? I started with nothing. I produce 0.45. What do I have at the end? Remember, I am forming products. So whatever I start with, I produce more by 0.45. And what do I have at the end? Of course, it's 0.45 because you had nothing at the end. The same thing is true here. So I'd have 0.225 at the end. And of course, all that's left for us is to calculate the concentration. Okay, they said our volume was 2 cubic decimeters. So we'll just simply say 1.55 divided by 2. And we get 0.775 Okay, 0.775. Remember, this is concentration. This is number of moles divided by volume, right? So number of moles divided by that volume of 2. Okay, so number of moles, so that would be x minus 0.225 divided by 2. So number of moles divided by volume. And what about here? 0.45 divided by 2, you get 0.225. Okay, and 0.225 divided by 2, and that would be the last one there. That's 0.1125. Okay, so those are the amounts that would have at equilibrium. Sorry that I made my table a little bit smaller, and it's affecting how it looks. Okay, right, now let's calculate quickly. They said we need to calculate Kc, right? Now I'm not too worried about that X amount. Why? Because that's a solid. And remember, when we calculate Kc, we do not include solids, isn't it? So I'm going to say, well, Kc, in this case, it's the molar concentration of my products. So what are my products? It's going to be hydrogen. So that's hydrogen. But remember, my coefficient becomes my power there. All right. So carbon dioxide, that's CO2. Those are both gases, so I'm going to include them, right, to the power 1, divided by my reactants. What are my reactants? It's going to be H2O, molar concentration of H2O. It's a gas, but the coefficient is 2, so I will square that. Okay, carbon, remember we don't include that in the Kc expression. And all that you simply do, ladies and gents, when you calculate Kc now, I'm going to substitute those amounts. And by the way, for those of you who still find this a little bit daunting, okay, please go and check our videos on Kc calculations, and I'm sure they will help you to navigate your way through this section. Okay, so now let's calculate. So note, now I'm moving from square brackets. Remember, square brackets tell us about concentration. Now I'm substituting the concentration. Hydrogen, that's 0.225. Carbon dioxide, that's 0.1125. Okay, and this we divide by the amount of H2O, that's 0.775. But remember, we are going to square that. Oh no, we forgot to square this part. Okay, right, and let's put that in our calculator. Right, we're going to make that as simple as possible. So that's 0.225, okay, squared times 0.1125, and we're going to say divide that by 0.775. Okay, and remember, we also need to square that part. Okay, right, I get 9.48. Okay, please, you can verify that for me. I know I've got my auditors out there who are always telling me, hey, you made a wrong answer. You got the wrong answer, sir. Okay, so that's times 10 to the minus 3. And remember, Kc does not have any units. Well, at least for now. Okay, so that was the last part. Okay, that was the Kc calculation. Now let's move on. Right, I'm sure that you've got that. You can verify if your answer does agree with what I got there. Okay, right, now let's look at the next section. So they gave us the graph. They say the graph shows how the rates of the forward reaction and rate of the reverse reaction change. Right, now they say give a reason why the rate of the forward reaction decreases between T0 and T1. Okay, now I want you to note there's the forward reaction there, and this tells you it's the reverse reaction. Okay, can you guess why that is the case? I mean, think about it. For the forward reaction to take place, what are you doing to the reactants? The reactants are getting smaller and smaller, right? The amount of the reactants are actually decreasing. So as a result, as the reaction proceeds, you decrease the amount of reactants, obviously it means that the rate of reaction would slow down. Right. So in if you think about it in particular, you had H2O there that was a gas, right? So in this particular case, that is what to change the rate of the reaction as you use up, the reactants, or rather, let me rather say the concentration of your reactants would actually decrease as you use them up, and so that would decrease the rate of reaction. Okay, right. Now they say to us, what change was made to the equilibrium mixture at T3? Now look at that. What happened? Both the forward and the reverse reaction increase equally. All right. The only reason for that, what would increase both the rate of the forward and the rate of the reverse? And by the way, I've got a very nice video that I have on, how to interpret, graphs of chemical equilibrium. Please go and check it under chemical equilibrium. Okay. Right, playlist, and you will find that help there. So what happened between T2 T3, right? It means that we must have added a catalyst, because it's only a catalyst that would favor both the forward and the reverse reaction equally. All right. So we added a suitable catalyst there, and then they say at T2 the temperature of the system is increased. So there it is at T2. They are telling us that the temperature is increased, right? And they're asking us, is the forward reaction exothermic or endothermic? So we need to now explain that part. Okay. Now, first of all, they are telling us about the change that took place. So look at this. When they increase temperature, you always need to look at that. When they increase temperature, look at which of the two reactions actually increased the most, or which was favored. Okay, look at that. They increased temperature, and the forward reaction just jumps up like that. What does that tell you? It tells you that the forward reaction is the one that is dependent on temperature. So the one that depends on temperature will be the one that will be affected the most. So therefore, it tells you the forward reaction is the one that depends on temperature the most, right? So therefore, what happens in this case? It means forward reaction is endothermic. So our answer to 9.3.3, we know this is endothermic. Okay. But in this case, what do we know? They say refer to Le Chatelier's principle to explain your answer. So I see this is 2 marks here, so I wouldn't really go as far as, just detailing, right? But what do we know? We know that an increase in temperature will always favor the endothermic reaction. Therefore, forward reaction must be endothermic. That's why it's favored, right? Okay, right. So that is how we are going to crumble this cookie. All right. I hope that you understood that. And for those of you who are still struggling in this section, ladies and gents, I've made all of those videos, just solely for your benefit. So please go and refer to them, use them as a resource. I've placed them there. At a point, these privileges will not be there. So if I were you, I would really, really maximize on them. Okay. But otherwise, I will see you guys again next time. And as I said, if you still need some help in this section, go and watch the videos. But if you don't, if you're not finding any joy there, or you're not finding any joy in anything else, by the way, mathematics or physical science, please send us an email at Mlungisi or info@mlungisinkosi.co.za. Otherwise, I'll see you guys again next time. Sharp, sharp.